Since 1900, every single earthquake to exceed a magnitude of 9.0 has belonged to one specific geological category, the Megathrust. The 1960 Valdivia earthquake in Chile reached a magnitude of 9.5. This single event released nearly a quarter of all global seismic energy recorded across the entire 20th century. In 1964, a 9.2 magnitude earthquake struck Alaska, violently fracturing the ground and dropping entire city blocks in a matter of minutes. These megathrusts represent a unique class of tectonic failure. They occur almost exclusively along the Pacific Ring of Fire, where specific subduction dynamics allow for unparalleled rupture scales. These massive 20th century ruptures forced a rethink of fault mechanics, providing the initial clues to how a single fault can store such immense potential. The engine behind these events is a subduction zone. This is a collision boundary where a heavy, dense oceanic plate is forced beneath a lighter, more buoyant continental plate. Typical faults cut vertically through the crust, but megathrusts feature a flat slab geometry, plunging at an incredibly shallow angle, averaging just 30 degrees. This allows the plates to scrape past each other along an unbroken line of contact, stretching for hundreds of miles. This immense overlapping surface area allows subduction zones to trap thousands of times more elastic energy than typical vertical faults. This massive overlapping surface does not slide smoothly. Instead, the plates get stuck in a specific region known as the Seismogenic zone. This zone has thermal boundaries between 150 and 450 degrees Celsius. Here, rock experiences velocity-weakening friction and locks tightly, even as the oceanic plate drives downward. The momentum forces the overriding plate to bend inward, accumulating strain like a giant compressed spring. This thermal frictional locking turns the overriding plate into a massive compressed trap waiting to snap back. When the friction finally fails, the compressed plate snaps back, sending a rupture spreading outward along the fault line at incredible speeds. A megathrust's final magnitude depends on the physical boundaries that force a spreading rupture to stop. During the 1906 Ecuador-Colombia earthquake, a massive 400-kilometer rupture was finally halted by creeping barriers, sections of the fault that exhibit velocity-strengthening friction, allowing them to absorb the shock. Evidence for these barriers appeared throughout the mid-20th century. In 1942, 1958, and 1979, this same 400-kilometer segment broke again, but in smaller, localized chunks because the barriers held the energy in check. In Alaska in 1964, oceanic sediment acted as a lubricant, smoothing out physical barriers and allowing the rupture to travel unimpeded for hundreds of miles. A megathrust's destructive potential is dictated by this hidden structural geology. Creeping barriers and sediments control whether a rupture dies out locally or grows into a giant. The devastation of the 20th century provided the global seismic datasets that allowed researchers to finally decode the megathrust cycle. This chart shows a diagonal spread of earthquake hypocenters, mapping the subducting Indian slab beneath the Burmese plate. These observations indicate that subduction events are predictable mechanical cycles governed by fault geometry and friction laws. Modern geophysicists use these mechanics to map the hidden asperities, the locked patches, and the creeping barriers situated miles beneath the ocean floor. Mapping these deep frictional locks allows us to identify which segments are primed for failure, offering a clearer picture of the scale and location of future threats.